Today on LokadTV, we're going to tackle the slightly new topic of differentiable programming. This exciting new development is the latest descendant of deep learning and has unlocked a series of challenges which previously were thought to be unsolvable. Today, we're going to learn a little bit more about this process and understand how this has led to rapid progress in the world of supply chains. So Janice, we're talking a bit today about unsolvable problems. Sounds fairly challenging, so what do we mean by an unsolvable problem?
I mean, what I mean is problems that are maybe not, that do not have, will not have a solution ever, but more like problems that do not have, unsolved problems that do not have a satisfying solution yet. And it's interesting because in supply chains, all problems are kind of solved, in a way. Obviously, factories are producing and people enjoy things that they can buy in stores, so the chain is actually working. But it might actually be working with significant inefficiencies. And until you've really wrapped your head around, you might not even see how inefficient it is at multiple levels. And especially when you start to think of variables of adjustment that you can use that are not traditionally used by, I would say, supply chain managers in general, such as pricing, assortment, all sorts of ways to kind of bend and twist the very demand of the market so that it's to bring the market closer to what you offer in a way.
Okay, so what sort of challenges, they might not necessarily be completely solved, but what sort of challenges are there that we've been sort of struggling with for a few years now?
So it depends on every vertical as its own set of, I would say, tough, poorly solved problems. So let's pick, for example, fashion. Fashion, obviously, and when I say fast fashion, affordable fashion, it's something that is the demand is very price sensitive. That's why all people, rush into the sales. It's because it's the point of time where you can have those super aggressive price. And obviously, due to the massive popularity of sales, obviously there are a lot of people who feel that it's worth, waiting hours and going to super overcrowded stores to benefit from those prices. So obviously, it's people want clothes and stuff that they like, but they really want them at a price they can afford. So, but bottom line is, you would say that obviously demand is super dependent on pricing, and yet virtually every single demand planning solution that I know of for fashion, except Lokad maybe, is treating demand as if pricing does not exist, as if pricing was a catalog price and this is it. While clearly, when you're pushing a product to the market, there is a whole pricing strategy that is going on. Where if the product sells, I would say, doesn't sell enough, you will trigger the sales and the discount to liquidate the stake and make room for the next collection to come. And so obviously, if you have something that is, in terms of process organization plus the software tech to support all of that, that is treating customer demand and pricing as things that are completely disconnected, there is obviously a massive gap. And it's clearly, even if it's hard to pinpoint exactly what is not solved, you clearly have an unsolved problem, which is a joint optimization of demand, stocking, and pricing at the same time.
So how is these dual problems kind of approached with existing methods? I mean, can we combine existing methods to get something that's satisfactory?
No, that's I would say the key is that most of the recipes that have been invented historically were not lending themselves to being blended into one another. That's kind of what s&op tried to do a bit, but at the human level. So let's have people talk to each other. With humans, it can work because they can talk, they're smart, etc. But when we are talking of software automations where the MRP is taking decisions, the WMS is taking decisions, stocking decisions, and then you have like an add-on on your PIM, product information management, that is controlling the price. All those systems, they don't have anything that is natively connecting them. And even if they do, it's not very clear at all with considering, the sort of methods that are used to generate the decision, stocking or purchasing decision on one side and pricing decision on the other side, that there is anything that you could just build in the middle to reconcile the decision and jointly optimize. It's at the core, those systems are designed with a divide and conquer mindset where what is not in the scope is just completely ignored. And that's how you can have recipes that are also way simpler.
Okay, so is this what differentiable programming is all about then? It's kind of a dual optimization that takes into account lots of different problems and kind of joins it into one?
Differentiable programming is conceptually the descendant in deep learning, but not as descendant as in more accurate for forecast. It's more like a different perspective on things. The recent progress that have been achieved by deep learning, where actually what people have been hearing most about it is the progress on the learning side. Indeed, there has been tremendous progress on the learning side. So for example, for pattern recognition in images, identification of objects, of people, or faces, and whatever. And that's very, very cool. And the progress has been very real. But there was also another side where deep learning just unlocked tons of and achieved tons of great results, which was numerical optimization. Why did we manage to recognize, with more accuracy, complex, image patterns, for example? It's because we were having models that were vastly more complex, much more parameters, in the tenth of millions of parameters, and then obviously to even train, which is figure out how you can build this mathematical model that is with a statistical process where you find the right value for this model to be very efficient on your data set. You needed to have like a numerical optimization recipe that was working at scale, because we are talking of millions of parameters to be optimized. And interestingly, deep learning, those so-called AI tech, but deep learning came with a series of breakthroughs on large-scale numerical optimization, which made possible many of the breakthroughs on the learning side. Differentiable programming stands, I would say, from a different perspective. It's what is of interest is both the fact that you can learn stuff from data, but that you can also have all the plumbing, the numerical, tools to do those large-scale optimization. And sometimes what you want is a mix of learning and optimization. It doesn't really make sense for, let's say, image recognition, where it's a pure learning problem. But in supply chain, you do not want as much as learning what will be the future demand, as much as taking the right decision that is optimized under an uncertain future, such as how many units do I buy if the supplier can make me this price. And then once I have the units that are being acquired, when should I decide to discount a specific product? So you see, it's both learning about the future demand, but also optimizing a variable where you have like a lot of freedom. And I'm obviously describing a process in case of fashion for one product, one price, one stock. But the reality is that clients do not come to a store for one product. They have needs and wishes, desires, and they are ultimately looking at the assortment. So it's not just, again, if you start thinking of those decisions that you could do on one product in isolation, one product at a time, you're kind of missing the point. And that's why all those brands need collections, because it needs to have like a raw assortment so that it starts to make sense for the clients.
Okay, so where does it work really well in kind of the real world then, that kind of learning and the optimization approach? What are the classic challenges that it's very good at sort of solving?
I mean, first, this tech is super new, and I think we have pioneered differentiable programming, so I would not say that there is like a well-established routine of where it's working very well. What I'm saying is that there are so many unsolved problems. So we've seen one in fashion, but actually there is so many other domains where you have similar problems that are kind of not resolved, and people have even stopped thinking about them. We discussed in DD MRP episode about the limitations of MRP and how DDMRP is basically duct taping fairly broken MRPs. But the reality is, what is the open problem that is not really solved? And to be fair to the credit of the DDMRP folks, if you don't have anything better to propose than DDMRP, then DDMRP is the best. So, what is the open problem that is kind of not solved? Here we have, for example, to perform an optimization under uncertainty. So you see, if you're performing an optimization like puzzle solving when you know the future, everything is static, not moving, and then you apply all your constraints, right, and you optimize. Yes, these sort of things have been solved since basically the 80s. Now, if you say that it's like under flux, completely stochastic, meaning it's like with third degree of randomness in it, then it's a completely different problem. And literally all the numerical optimizers that we have just falls apart. And that's why DDMRP say, well, because we don't have anything that works in those conditions, let's fall back on super simplistic recipes with decoupling points and decoupled lead times. But you see, that's the consequence. The MRP is the consequence of lack of proper tools to actually properly tackle the problem. And then we can go on, just think another angle where it's clearly there is literally industries, entire industries are missing the point. Fundamentally, when you think in terms of demand forecasting, every single unit that you sell is connected to a client. Nowadays, thanks to loyalty programs, pretty much every retail chain, obviously every single e-commerce from the very start, but pretty much now even every single retail chain through loyalty cards have the identification of the client. So they know exactly who purchased what at which point of time, under which conditions, what were the products when you purchased a product in the store, what were the products that were present and the one that were not. So they know that you did a choice that was limited to what was available at this point of time. So there is a lot of information here that I've just described. The assortment at the point of time of the purchase decision, and the identity of the clients who has a whole history of purchase, even if it's a short history of just let's say, a couple of times of purchasing something from the chain. And nowadays what I see is that literally there is like zero solution on the market that is even using this data. So again, in terms of unsolved problem, there is clearly a massive potential, and I'm not talking of exploiting social media or exploiting, Instagram for social media analysis. I'm talking of something that is very blunt. That's something like every single large retail chain has. It's data that they have, and it obviously contains truckload of information about what people want at which time extra, and yet it's not used at all. So clearly there is, again, this disconnect. And again, differentiable programming was kind of a source of inspiration to say, how can we even start thinking about those problems?
Okay, and what about those sort of mysteries that are still out there? I mean, I love this idea of an unsolvable problem. So what are the real sort of challenges in a supply chain that differentiable programming doesn't even scratch the surface of?
Obviously, there is all the wicked problems. So the wicked problems will probably not be solved before the advent of what is called strong AI, so human level intelligence. So what are those wicked problems? They are mostly the idea of thinking about second order consequences of your actions. So what do I mean by that? For example, when you do promotions in a brand, fashion brand, well, you're doing two things. You're liquidating your stock, which is good. That can be optimized with, jointly with differentiable programming, so that you think about that right from the very beginning when you order to your supplier your first units. Okay, good. But then what the second order consequences are the fact that when you do promotions, when you do sales, you're actually training your customer base to only shop from your store, your chains, or your e-commerce only when it's on promotion. And there might be a drift that happened for over a decade where you transition from people who are very happily buying, all the time, to most of your clients who now only buy on sales. And you see, it's like a self-fulfilling prophecy. And clearly right now, and why is it called, you can check the Wikipedia page, those sort of poems are called wicked. because fundamentally the component is that we are not dealing with automatons. Your clients are not automatons. They are smart and they adapt. So basically, you need to think about the fact that when you do something, people will think and adapt to what you're doing. And so that's what I call those second-order consequences, is that when you do something, people know that you're going to do this thing, so they have expectations, so they expect to do that. So themselves, they adjust their expectation and what they do based on what they think about you. It's a game of I'm thinking what you think that you think and whatnot. This sort of recursion. And it's something very human that humans are actually quite good at doing. And it's all those wicked consequences. Another solution, for example, would say, you're, let's say, a car manufacturer. You thanks to your super good supply chain, you improve the supply chain for the distribution of car parts and for your own network of garage, and you improve and your garage becomes so good that you actually alienate your historical partners in this market. So you do an optimization on one side, and then you piss off important partners that were your historical partners. So it's like, should you give up on optimizing your supply chain just to keep your partners happy? Maybe, maybe not. Again, that's the sort of kind of wicked problems where right now it's completely beyond any capabilities of any algorithm that I'm aware of. Even the most fancy AI stuff that you read in the press is nowhere close in even scratching this sort of wicked problems.
Okay, sounds like those wicked problems are probably a problem for the differentiable programming of tomorrow.
Skynet from Terminator, that's more like what it takes to solve those sort of problems.
So why was now the time to sort of look back at some of these unsolvable problems? Well, what's changed in the world of technology that meant that differentiable programming could now sort of make this progress?
It literally the fact that we have gone from technology where we could optimize, models with literally a few hundred of parameters to model that can have 100 million parameters. That's what you get with modern, deep learning technique, recycle for optimization purposes in differentiable programming context. That's game changing, because the challenge was many of the clients we are discussing with, unless they are really like baby companies, super small shops, they have problems that are kind of at scale, even they are not Walmart. As soon as you have like 50 stores, problems need to be solved at scale. And 50 stores, if you have 10,000 products, per store, we are talking of 500,000 SKUs. So it's like 500,000 variables for pricing and stock decisions like every day. So it grows very fast, very quickly. And again, so what changed was when we went from those capacity to optimize problems with a few hundred variables to millions, suddenly it made feasible the resolution of tons of problems that were just like completely infeasible. And interestingly, was deep learning was a combination of hardware progress and software progress. So hardware is still progressing fast, better CPUs with more cores, more raw processing power. It's still progressing relatively fast. But on top of that, where it was even faster, that there was a series of breakthroughs where you had a hardware that was, let's say, giving you 10 units of processing power. 2 years from now, you will maybe have 20 units, or maybe that will be 3 years from now. Okay, so that's a nice exponential progress over a period of, let's say, 3 years or something. But if every 6 months you have like a software breakthrough, a mathematical breakthrough that double the efficiency of the algorithm that you have, then your progress is dramatically faster. And that's exactly what has been happening with deep learning. There was like a steady progress of the hardware, but it was completely amplified by a series of, I would say, of breakthrough that were more on the algorithm mathematical side. That were you literally had twice as much horsepower from the same hardware. So the acceleration has been like, all of that has been like happening during the last decade. And the result is that we went from models with a few hundreds variable to hundreds of millions in a within a decade. I mean, not exactly, but that gives you kind of a frame. So this is what changed. I would say a large portion is just to be able to apply that at scale with agility, because and cheaply also as well.
And is that growth going to continue, or is it something that has actually grown as much as it kind of needs to now?
Yeah, I mean, that's the point, is that I think we have reached the point of diminishing returns right now. I mean, at Lokad, most of the problems that we face are not literally the fact that we are short on processing power. We have like excess processing power. We don't have problems that we say, if processing power was 10 times cheaper, we could do it. I would say it's very rare, and when we have methods where we could literally invest a lot more processing power to get a little nudge, it's typically exceedingly marginal. You can have a few 0.2% extra accuracy by investing 10 times more CPU, but it's just not worth it. You better rethink the whole thing.
Okay.
So I believe that now the main challenge lies in the kind of expressiveness, how you make those problems that are open fit into any framework. And why differentiable programming? It's rather the opposite. Differentiable programming is literally trying to target maximal expressiveness. So that's through maximal expressiveness, you can have a lot of things that were like open problems so far that just happen to enter the realm of the stuff that you can do with differentiable programming.
Okay, let's start sort of bringing things together then. In terms of differentiable programming, what does it mean for the supply chain practitioner? What are the sort of benefits that they're likely to see from this, and how is it going to change how they're currently approaching problems?
I mean, that will be one massive step forward in getting rid of silos. We made an episode, I think it was like 20 episodes ago or something, on all those silos where we had vertical and horizontal silos. Well, the reality is that I was saying, well, we should just get rid of those silos. But the reality is that maybe people could object is, yes, but it makes sense, because obviously there is like untapped inefficiencies that could be just removed and optimized away if we are able to do that. But the tech is just not there. So for now, we are stuck with our silos just because for lack of alternative. So I believe that differentiable programming very concretely opened the door to think of joint, pricing plus assortment, or assortment plus purchasing, or assortment plus pricing, or purchasing plus pricing, or you see all sorts of problems that were solved in isolation, and then you can now say, oh, we are going to solve them jointly, which is going to also require to kind of reinvent the way those companies are organized, because those silos of old will not, survive this new world when companies start to go, I would say, the Amazon way of just blowing up those silos and cross-optimizing those domains.
Okay, brilliant. Well, thanks for your time today. So that's everything for this week. Thanks very much for tuning in, and we'll see you again next time. Bye for now.